We're going to take some time today and go back and review our kinematics unit, which is a long, long time ago. Back in February, we started this. The first day of kinematics, we defined two terms that you would have looked at in Science 10 before as well, a vector versus a scalar. Who remembers the difference between a vector and a scalar? Emma? Right. Magnitude and direction is a vector, and a scalar is something that has only magnitude. Now, we talked about 5 different terms that were examples of vectors and scalars as well, and we defined distance as a scalar, position as a vector, displacement was a vector. Let's go with those 3 first. Distance was simply how far something moved. Okay, if I go 39 kilometers to downtown Calgary, if I go 15 kilometers to High River, if I go 112 meters to the math wing, okay, that's distance. Okay, that's not, there's no direction associated with that. If I go 400 meters around the track outside, that's just the distance traveled. Position is what? It's a lot like distance, right? But it's not the same thing as distance. What's my position defined as? If you can't remember a definition for something like that, like let's just logically think about what it could mean. If I say, what's your position? Your answer might be, Rosie, what? Yeah, it's where you are relative to a certain point, right? I might be 10 meters from the back of the room. I might be 100 meters from the football field. I might be 39 kilometers south of Calgary. Position is where I am relative to something. So we always need that frame of reference. Or that relative point, relative to something, right? Relative to Calgary. I'm 30 kilometers south of Calgary. I'm 15 kilometers north of High River. 100 kilometers west, or sorry, east of Banff, or whatever the case may be. Displacement, a lot like position, but it's the change in position. So if position is D with the arrow over it, displacement would be delta D, the change in position. You guys remember there's 2 ways to find displacement, depending upon what we have. If you have 2 displacements already, then the total displacement would be the first displacement plus the second displacement. Or if you have 14 displacements, then it's the first one plus the second one plus the third one, and so on, all the way up to the 14th displacement. But if you don't have displacements already, but rather you have positions, then we would say it's the final position minus the initial position. So for instance, let's say that I am 4 meters from the front of the room, 4 meters north of the whiteboard. Okay, I'm 4 meters north of the whiteboard. Now I'm 9 meters north of the whiteboard. What's my displacement? Do I add those or do I subtract those? Add them or subtract them? What do? Add those or subtract them? I was 4 meters north of the whiteboard. Now I'm 9 meters north of the whiteboard. Do I add those 2 numbers or subtract them? What was I given there? Was I given displacements or was I given positions? 4 meters north of the whiteboard. What is that? Displacement or position? That's position, yeah. So if I've got 2 different positions, 4 meters north of the whiteboard and 9 meters north of the whiteboard, then I'm going to subtract them to get 5 meters to the north. My displacement is 9 meters to the north minus 4 meters to the north, which is 5 meters to the north, right? Subtract them to get displacement. What if I said I walked 4 meters to the north and then I walked 9 meters to the north? Now those are 2 different displacements, right? Not where I am, but how far I've gone. So if I want to find the total displacement there, then I'm going to add them up, right? So in the first case, it would be 9 minus 4 is 5. In the second place, it would be 9 plus 4 is 13 meters is my total displacement. You understand the difference there? What if I say 4 meters to the north and 9 meters to the south? 4 meters to the north and 9 meters to the south. Let's say I walk 4 meters north and then I walk 9 meters south. What's my displacement now? Rosie? Good. You add them up, but the second one will be negative. So the answer there would be negative 5 meters or 5 meters to the south. That would be my displacement. Still add them up, right? Still add them up, but you have to include negative values there. Let's distinguish between distance and displacement here for a second. In the first case, when I said I walked 4 meters to the north, and then I walked 9 meters to the north, my distance was 13 meters. My displacement was 13 meters as well. But in the second case, I walked 4 meters to the north, and then I walked 9 meters to the south. My distance was 13 meters, because I don't pay any attention to direction now, right? My displacement, sorry, was negative 5 meters. Why is distance sometimes the same value as displacement, as it was in the first case, but sometimes a different value than displacement, as it was in the second case? Why was it 13 and 13? Then why was it 13 and negative 5? What was it? Yeah, that's right. Fundamentally, mathematically, you're right. Because with displacement, you can have negative values as well, and you can't have negative values with distance. Sure. Okay, in the end, what's the big thing there? Yeah, when I change direction, distance and displacement will be two different numbers. Same goes with velocity and speed, as we're going to talk about a little bit later on, right? If I keep going in the same direction, the number for distance and displacement will be the same number, except displacement is going to have a direction with it, right? But if I switch direction, then those two numbers are going to be different. Then we talked about speed. Speed's how fast something travels, and it's related to the distance. The units for speed, by the way, almost always going to be meters per second, although we can use things like kilometers per hour, but usually we go with meters per second because later on, as we start talking about acceleration, then we've got to use meters per second. Velocity is related to displacement. So speed is related to distance, velocity is related to displacement. In other words, speed is a scalar and velocity is going to be a vector because it's related to displacement. In those two definitions, the rate of change of position, how quickly something travels, both lead us to our group A equation, the only equation we have that are valid for constant speed / velocity. V is equal to delta D over delta T. Some of you on your West Edmonton Mall assignment, I've noticed this, is a lot of people have asked me questions about things. That's good, by the way. The more questions, the better. Keep asking those questions over the next couple of days until it's due on Monday. Some of you, for one of the rides, I think it was the space shot where you had to find the acceleration of the space shot upwards. There's a lot of you that tried using V is equal to delta D over delta T to get V, and then you used A is equal to delta V over delta T in order to get the acceleration. That's wrong. Why is that wrong? Can anybody explain to me, when we were looking for the acceleration of the space shot upwards, why is it wrong to use V equals D over T and then an acceleration equation? What kind of problem do we have when we're looking at a space shot accelerating upwards? Yep. It's not at a constant speed. That's a group B problem, isn't it? Okay, we're only allowed to use V equals D over T in a group A problem if it's going at a constant velocity, or if you're looking for the average velocity, okay, then it's a group A problem as well. But if it's involving acceleration, then you can't do that. It's as simple as that. You might look at it and say, oh, I'm tempted because it's so convenient to find V using D over T. It doesn't matter. And you find it all you want using V equals D over T. It's wrong. So it might be convenient, it might be handy, but it's wrong unless you've got a group A problem. So anytime you involve acceleration, don't use group A. I'm going to write a little note there. If acceleration, don't use group A. Don't use V equals delta D over delta T if it's an acceleration problem. Things are starting to get a little crammed together here. Let's start just breaking it up a little bit for us here. There we go. Well, then we talked about acceleration. I've changed the order of this just a little bit from what we did, the way we did it in class. That's okay. It's just not going to match up quite perfectly chronologically with the way that we did it in class. That's all. All right, let's go on and talk about acceleration here now. Acceleration is a vector, right? Because it's the rate of change of velocity. It's how quickly your velocity changes. It's not how much your velocity changes by, right? A charged particle can accelerate at an incredibly high rate for an incredibly short period of time and reach an incredibly high velocity. But it could also accelerate at an incredibly high acceleration for an even smaller time and reach a pretty small velocity. The change in velocity is not the acceleration. You can have a really high acceleration, have a low final velocity, or vice versa. Okay, acceleration is the rate of change in velocity, how quickly velocity is changing. And the basic equation for that one, if you remember, was our first group B equation. A is equal to delta V over delta T. It's not, guys, it's not V over T. It's not V over T. It's delta V over delta T. It's the change in velocity. So if you've got a problem where you've got a velocity, that's great. Don't use it unless you've got two velocities. Now, a lot of times the final velocity or the initial velocity will be zero, okay, but not always. That's the basic definition. The units, by the way, for acceleration, meters per second squared. And of course, we've got a bunch of other equations that we're allowed to use here along with this one as well. We've got VF squared is equal to VI squared plus 2AD. What does VI stand for there? VI in this equation. Oh, can we get this one, Reese? Good. Initial speed, not initial velocity. Okay, initial speed because it doesn't have a vector sign over it, right? We have D is equal to VI plus VF over 2 times T. We have D is equal to VIT plus 1/2 AT squared. And we have D is equal to VFT minus 1/2 AT squared. Go back to our field trip project for a second, the one that's due on Monday. I was talking to somebody yesterday about this at lunchtime. He was asking some questions on it. He was analyzing, once again, the space shot, and he was trying to find the acceleration. He recognized, good for him, he recognized that he wasn't allowed to use V equals D over T. So he was trying to find something to find the acceleration of the space shot as he was avoiding using a group A equation on it, using V equals D over T. So this is the one that he came up with. That's a perfectly valid equation to describe the acceleration of the space shot as it rises upwards. But what's the problem with using that acceleration? By the way, he set VF equal to 0. He said, but I said, well, that doesn't work. He said, well, how come? Because when the space shot goes to the top, it stops, right? So what's the problem with using VFT, recognizing that VF is 0, VFT minus 1/2 AT squared to find the acceleration as the space shot accelerates upwards? Yep. Good. Yeah, really what you got there is two problems, right? Two phases to a problem. As the space shot goes up, it accelerates. It speeds up as it goes up. And then when it reaches close to the top, what happens? Well, it's got to slow down. Think about that. It can't stop if it doesn't slow down. If it was moving and now it's not, it's slowed down. So we've got two problems there. The acceleration, which is what we're actually looking for in that problem on our assignment, and our deceleration phase right here, which is where it's slowing down to a stop. If you're analyzing the deceleration phase, then go ahead, use this one, VFT minus 1/2 AT squared, because you know what the final velocity is right there. Okay, you know that VF is equal to 0. But if you're using this one, you can't use VFT minus 1/2 AT squared because I don't know what the final velocity of that stage is. I know what the final velocity of the whole thing is, but not this stage. And remember that this is two separate things happening, so we got to analyze them separately. Okay, this is what you were asked in the assignment. We don't know what VF is for that part of the problem. The fact that we do know what VF is up here doesn't really matter, because that's not what the problem is. All right? By the way, while we're at it, okay, this is completely relevant to what we're reviewing here. What would you use? What likely would you use to find the acceleration of this space shot as it accelerated upwards right here before it started slowing down, reaching its peak height? Yeah? Or plus 1/2 t squared. Yeah. VIT plus 1/2 AT squared. We know what VI is. VI at the bottom is 0. It's okay to say that because that's part of the same problem. It starts at 0. And then we turn around and solve for acceleration given the displacement and given the time there. Okay? Good? Be conscious of things like that, right? It's okay. These are all valid equations every time we have an acceleration problem. But understand that we got to get our givens right. We got to nail our givens in order to use them properly. If it's constant velocity, use the first one. If it's acceleration, use one of the other 5 equations, but make sure you use them properly. Those are my group B ones. Those are, lots of you guys have those circled on your data sheet. The data sheet that you get on your exam, by the way, will be exactly the same as the data sheet that you guys have right now. So if you make notes on your data sheet and you kind of learn where things are and discover patterns on your data sheet, whatever, okay, go with those because it's going to look exactly the same way on your final exam. One more thing before we give an example. We talk about acceleration and the rate of change in velocity. One area where we use acceleration a lot is with gravity. Gravity caused by the Earth causes things to speed up or slow down depending upon which way it's going. Generally, we're going to make the acceleration due to gravity on the surface of the Earth negative 9.81 meters per second squared, whether the object is rising or whether the object is falling. Now, this is only in the context of gravity and only in the context of the Earth. But why is it? Can you explain to me why, as, let's say, the board marker rises up into the air, we say it accelerates at negative 9.81, but as it falls back down and speeds up, it also accelerates at negative 9.81. How can we say it's the same value, both negative 9.81, when it's going in both directions, upwards and downwards, Riley? Good. When it's going up, it's slowing down. When it slows down in the positive direction, it's a negative acceleration. And good. When it speeds up in the negative direction, it's a negative acceleration as well. All right. So now you can encounter group B questions where you've got conceivably an acceleration of negative 9.81, maybe not given to you in so many words, but you can recognize that that's the acceleration. Don't always make that the acceleration, only if the object is rising or falling under the influence of just gravity. All right, so let's do an example now. The question says a 2 kilogram ball was thrown up into the air at a speed of 12.5 meters per second. What is the maximum height of the ball, and how high does the ball go before it stops and turns around and comes back down to where it started? And what's the ball's average velocity during that time? Remember when we tackled these questions way back in February and March when we were working on these? The first thing we did is not so much look at our givens, although those are important. The first thing we did was not so much find an equation per se, although that's important. The first thing we did is identify what type of problem we had. If it was a group A problem or a group B problem. What do we have here? Group A or group B? Is this a problem that involves acceleration or not? Rosie, what do you say? Yeah, we say group B because it involves acceleration, right? Now, there's two things we're being asked for here, right? There's the maximum height of the ball and there's the average velocity of the ball. We're going to make the maximum height of the ball a group B problem because it's slowing down as it rises up into the air. But when we're looking for the average velocity, remember, average or constant velocity is group A. So we're going to actually make this both, group A and group B. But remember, as we're solving one, we've got to keep it completely separate from the other one. First, our group B problem. What do we got given to us here? We have a mass of 2.0 kilograms, and we have an initial velocity upwards of 12.5 meters per second. We're looking for the max height of the ball. What variable would you say we're looking for here? A, V, X, Y? What are we looking for there, Nick? Yeah, we're looking for delta D, the displacement, right, at its max height. Is there anything else that we have if we read between the lines? That it? What is it? What is the final velocity? The final velocity would be 0, yes. If we're analyzing the max height, right? If we're analyzing the trip up and down, then it wouldn't be 0, right? But at maximum height, it stops when it reaches that max height. So let's get delta D here now. What equation do you want to use from our list of group B equations? Because this is a group B problem, right? What equation do you want to use here? Let's maybe try, I don't know, VF squared is equal to VI squared plus 2AD. That seems to be so often the one we end up using. We're going to solve for delta D here. VI goes over by subtracting. VF squared minus VI squared over 2A equals delta D. VF is 0 squared minus 12.5 squared over 2 times, oh, what's A? What's A as it goes up into the air? Negative 9.81, good. Equals delta D. Let's figure that out now. So 0 squared minus 12.5 squared, of course, equals, and let's divide that by brackets 2 times neg 9.81. And we get 7.9638. Maximum height to 2 significant figures would be 8.0 meters. So the ball's average velocity. Remember, that's a group B problem, group A problem, average velocity. We could say V is equal to delta D over delta T. Do we know what T is? Maybe we got to find it. How are we going to find T? Well, other than finding the average velocity, it's a group B problem. So let's use another equation to find T. Let's say something like, I don't know, A is equal to delta V over delta T. Delta V is what? Final 0 minus initial 12.5 over the acceleration of neg 9.81. So we're going to say delta T is 12.5 divided by 9.81 gives me 1.274. All right, there you go. That's how long it takes to go up there. Now, because I'm looking for average velocity, which makes it a group A problem, we can say 7.9638 divided by 1.27 seconds, and we end up getting 6.25. Good. Anybody think of another way to find average velocity in this case? Which doesn't always work, but does in this case. Yeah. 0 plus 12.5 divided by 2 gives me my average velocity, and we get 6.25, right? That works here. That works because it's the same thing happening the whole time. It's a deceleration of 9.81 the whole time. But if something different happened, you were speeding up, then slowing down, then traveling at a constant velocity, then speeding up again, and you wanted to find the average velocity, you have to, in that case, take the total displacement divided by the total time. Okay, good. There's 3 types of graphs we looked at. Let's look at the acceleration time graph first, because that's the easiest one. Honestly, it's the easiest one because you don't have to do much with it. You just have to know a couple shapes for acceleration time graph. Maybe we see an acceleration time graph that looks like this. That's a constant acceleration. Maybe we see an acceleration time graph that looks like this. That's an increasing acceleration. Maybe we see an acceleration graph that looks like this. That's a decreasing acceleration. Not a decreasing velocity, but a decreasing acceleration. It's not slowing down. The rate at which it speeds up is decreasing. We don't have to do any calculations with those. If you see something like this, an acceleration time, it would appear as part of your multiple choice. Now, position time graphs, we've got to know the shapes of them. But we've also got to be able to do calculations with them. And I'll tell you right now, there is a question. It's question number 2 on the written portion of your final exam. That is a graph. Question number 2 on your final exam is a graph. I'm not telling you whether it's a position time graph or if it's a velocity time graph, but you can see that there's some questions that follow it. You're going to get a graph, one of these two, as question number 2 on your final exam, where you're going to have to find out the displacement, the average velocity, the whatever. So let's go through that here now. All right? Let's say we got a position time graph that looks like this. There's a number of things that we can find from this position time graph that you have a 50% chance of having to find on your final exam, because you know you're going to get one of these two graphs. First thing you got to find is the position at a specific time. Second thing you've got to be able to find is the displacement over a period of time. Third thing that you've got to be able to find is the velocity during a certain stage. The fourth thing that you can find is the average velocity over the entire trip. How do you find position? How do you find the position? Let's say at this moment in time, I want to know where it is right now. David? Yeah, and then? Good. So it's up and over. How do you find the displacement? How do you find the displacement on that graph? Let's say I want to find the displacement between, I don't know, let's say here and here. What's the displacement there? How do we define displacement? David? Okay, be careful. It's not the smallest minus the largest. It is in this case, but only by coincidence. What we do is take the final minus the initial. Okay, what we got to do is take final position minus initial position. You know how to find position, right? You just told me it was up and over. So you're going to go up and over, and then say final minus initial. Final position minus initial, minus initial position. Now the velocity in one stage, the easiest way to find out is probably going to be displacement divided by time. You just found out how to find displacement, right? This flows, right? You can find position, and then from that you can find displacement, and then from that you can find velocity, because velocity is displacement divided by time. Average velocity? Well, for the entire trip, we'll say the entire velocity, or the average velocity, is once again displacement divided by time. But it's the total displacement this time, the final minus the initial divided by the time. What would be the average velocity? Real quickly, the average velocity in this graph, even with no numbers. What's the displacement of the object in this graph? 0. So the average velocity would be 0, back where you started, right? So we got a velocity time graph now. We got a similar shape here. Looks like this. What do we got to find from this one? You got to be able to find the velocity at a specific moment, the change in velocity, the acceleration, and the displacement. Velocity is up and over. Just the same as position was before. The change in velocity is final minus initial. So up and over, subtract the 2. Acceleration is A is equal to delta V over delta T, the change in velocity over the time. So again, this one flows as well. If position time graphs went from position to displacement to velocity, finding the position gives you displacement, finding the displacement gives you velocity, then this is the same thing. Finding velocity gives you the change in velocity, finding the change in velocity gives you the acceleration. Yep. Delta V over delta T? No. It's all good there. And finally, displacement. How do you find that? This is the toughest one to do. This is the one that everybody always makes mistakes on. On a velocity time graph, displacement is the area. On a position time graph, it's easy. It's final minus initial position. But on a velocity time graph, you've got to find the area. Okay, you will, I promise you. Question number 2, written response portion of your final exam. You're going to open it up. You're going to see question number 1, by the way, is a projectile motion question, which we'll talk about later on here. Question number 2 is a graphing question, either position versus time or velocity versus time. And it's worth 2, 3, 4, 6 points. I think the test is out of something like, I don't know, 80 or something like that. There you go. There's 6 points right there. There's almost 10% right there if you can do that. The real trick is here, don't get them mixed up. Don't get position and velocity time mixed up. Okay, keep them straight. It should be good. All right, let's keep plugging away at this, all right? Now we're getting into two-dimensional kinematics, two-dimensional motion, right? Where we talked about adding two-dimensional vectors, adding position vectors, adding velocity vectors, displacement vectors, adding velocity vectors. Okay, in the end, remember, when we're adding two-dimensional vectors, the goal, always the goal is to get a right-angled triangle. And why do we want the right-angled triangle? Because when we have a right-angled triangle, we can use the Pythagorean theorem and the tan function to get what we're looking for. Right? Get a right-angled triangle. Sometimes you've got a question where you have a right-angled triangle. If you have something like this, great. Let's say this is 4, this is 3. We can solve for the hypotenuse here, the resultant vector, by saying it's the square root of 3 squared plus 4 squared. Ends up being equal to 5, right? Easy. Okay, you find theta, which is always drawn at the start of it, by saying the inverse tan function of 3 over 4, sorry, which gives me whatever angle that is. Okay, if I've got a right angle triangle, good. All you're going to do is the Pythagorean theorem in the inverse tan function. But if you've got, let's say, 3 vectors like this, 4 plus 5 plus, let's say, 1 plus 1 this way, what are we going to do? This is when we got to break into the x and y components, because remember, the goal is to get a right angle triangle. So we're going to say x components, y components. We're going to say 0 and 4, 5 and 0, 0 and minus 1, minus 1 and 0 for the y component. They add up to give me 4 and 3. So we're going to say 4 on the y-axis, sorry, 4 on the x-axis, I should say, and 3 on the y-axis. And we can find that resultant vector because we know we have to use the Pythagorean theorem and to find the angle of the inverse tan function. Exactly what we did over here, because now we have a right angle triangle. So if you got this, okay, don't worry about that. Get this. If you've got this already, great. Bottom line is, when we have that right angle triangle, we always do the same thing, the inverse tan function and the Pythagorean theorem. Sometimes it looks a little bit more complicated than the second example here. Okay, sometimes you get a funny angle. A funny angle is an angle other than 90 degrees. So what do we do if we have something that looks like this? We want to find the resultant vector there. Well, 5 words that we usually say that come to our mind whenever we see a funny angle. What are they? It's been a while since we've seen this now. What are those 5 words, Miles? You remember them? I don't like funny angles. So let's get rid of it then. If you don't like funny angles, let's get rid of it. Let's take the 5 over off to the side here and get rid of it. This is x, this is y. Let's say cosine 30 degrees is equal to x over 5. Let's say sine 30 degrees is equal to y over 5. Get your number for x and for y. And then do your x components and y components. Remember, what you probably should do at this point, once you get your x and y for that, let's literally replace that with this. And then we add up the x's and y's. Get a total x and a total y like we did over here. And then do the Pythagorean theorem in the inverse tan function. Remember, even when we have a funny angle, the goal is to get a right angle triangle. It means one extra step, that's all. Here we started with a right angle triangle. We did Pythagorean theorem in the inverse tan function. Here we started with right angles, but not a triangle. So we did x and y components. We got a right angle triangle, did the inverse tan function and the Pythagorean theorem. Here we had a funny angle. We got rid of the funny angle. Then we did x and y components. Then we did Pythagorean theorem in the inverse tan function. So again, it kind of flows, right? We start off with the easy question where we just do solve for r and theta. Here we have a harder question, get x and y, solve for r and theta. Here we have an even harder question, get the components, then get x and y, and then solve for r and theta. But it kind of logically flows from one type of problem to the next. Talk about relative motion and navigation. Same type of vector analysis here there. But what you got to remember with relative motion navigation is that we have 2 types of lines. We have solid lines and we have dotted lines. The solid lines would be things that contribute to where I go, the contributing vectors. For example, wind speed, river current, aiming in a particular direction, heading in a particular direction. All of those things contribute to where I go. My dotted line vectors are where I go. They're resultants. They result from the contributing vectors. Where do I end up going? Well, I end up going somewhere because of the wind and because of where I aimed. The solid line vectors are the wind and where I aimed. The dotted line vector is where I ended up going because of the wind and where I aimed. If I head to the north, if I aim to the north at 30 meters per second, that's a solid line vector. If there's a wind to the east at 20 meters per second, that's a solid line vector. Where I go, the resultant is a dotted line vector. I end up going somewhere north and east there. And once again, I can find that by using the Pythagorean theorem in the inverse tan function. If I want to go north, that's not contributing to where I'm going. That's where I'm going. If I want to go north, then I would make that a solid line vector. If there's a wind blowing to the west, sorry, a dotted line vector. If there's a wind blowing to the west, I'd make that a solid line vector. Where do I have to aim? I would have to aim right here as a solid line vector. Make sure it's drawn, solid line vector is drawn front to back or head to tail, and the dotted line vector drawn start to finish. Again, use the Pythagorean theorem or the inverse tan function to figure out where you got to aim. Question number 1 on your final exam will be one of these two questions. It will be where an object is launched horizontally off the edge of a building or a cliff like this, or it will be one of these situations where the object is launched this way at an angle off the ground and ends up downfield somewhere. Now, you need to be prepared for both. You will see one of them on your final exam. In both cases, we set it up the same way. I don't want to see anybody on their final exam not writing this down next, because it's going to be the way that it is. X and Y, whether we're talking about the angled projectile motion questions or the horizontal ones, it's X and Y. What equation do I use always to describe the X component there, Natalie? You remember which one it is? No. That's okay, guys, if you can't do it right now, because it's been a while, right? I didn't give you a chance to prepare for this one. Okay, I'm giving you a chance to prepare for 12 days from now on your final exam. Okay, in 12 days, we've got to be able to answer that question. Okay, what equation do we use to describe the X component? Always the same. Delta D over delta T. And the reason is because it's constant velocity. Whether it's going this way or whether it's going this way, it's a constant velocity. You will start off like this. The very first thing you'd write down, besides maybe your givens in a picture on your final exam, will be that equation. What's the second one? The Y component? Stefan? Remember that one? No, don't remember? Christian, you remember the Y component here? No? Anybody? I know it's been a while here, but Emma? Good. AT squared. Good. Excellent. We're going to do the same thing for both. That will be the second thing that you write down on your final exam in 12 days. You need to write down both of these equations because whichever form you see, it will always start off with these two equations. Now, you sub in numbers, right? Let's say this velocity right here was 10 meters per second and the height was 20 meters. Let's say this velocity is 10 meters per second and our angle is 30 degrees. We would make this speed 10 meters per second. Delta D, we don't know. Delta T, we don't know. Delta D for the Y component is neg 20. VI would be 0. And A would be neg 9.81. You'd probably solve for the time here. Plug it back into here and solve for the horizontal displacement. For this one, you would first look at this and say, oh, wait, I got a funny angle. And I don't like funny angles. So we'd get rid of it the same way as we did on the previous page, right? Break it up into X and a Y. Get rid of the funny angle. Take the X value, plug it in here for the X velocity. Take the Y value, plug it in here for the initial Y velocity. Sub in some numbers. What's the same about these questions? Almost everything. What's different? This is different. For the horizontally launched, it's just the number you're given. For the one that's launched at an angle, you got to find a component. Okay, it's an exponent using the cosine function. What else is different? This number. For these problems, that number is 0. For these problems, that number is, once again, a component of your initial velocity. What else is different? This. This is negative 20 in the first example, negative something always. What is it in these problems? The y displacement is 0 because we land at the same place that we started vertically. So those three variables are different, right? This is just a number that's given to us. This is a component. This is 0. This is a component. This is negative something. This is 0. Remember those things, plug in your numbers. You should be able to nail this every single time. Now, there is one more thing that we sometimes have to do with the bottom problem, and that is to find the max height. We won't have to do that with the first one, right? Because tell me right now what the max height is for the first one. 20. You can't go any higher if you're not launching it up into the air. It's 20. What's the max height for this one? I'll put that in purple because, once again, this is a little bit different than the first problem. To solve for the max height, you're going to say VF squared is equal to VI squared plus 2AD for the Y component. You're going to solve for D, and you're going to set VF equal to 0 because vertically it stops at its max height. VI, well, that would just be this number right here. It would be the Y component of that velocity that you found.